Okay, welcome back. So, real gases, they're fun, they're what you actually end up working with in, reality, but ideal gases are a lot simpler and easier to play with, so let's keep on doing that. We now will move on to talking about gas mixtures. Okay, so what happens if you mix two gases? Well, each gas pretty much just ignores the other one in one sense. Or they act like the other one is exactly the same as itself. The individual particles are incredibly small. They don't interact except to collide. So it doesn't really matter if it's colliding with another particle of the same gas or of a different gas. Okay, so they'll just move into one another's space. They'll mix perfectly, and then their pressures will add up. This is what's known as Dalton's Law of partial pressures. For those who are curious, yes, this is the same Dalton as the one who confirmed atomic theory. He was a well-studied individual. In fact, he was also famous for his work on gases. All right, so let's go ahead and take a look at an example of what happens when you mix two gases. Specifically, we are going to mix 2 grams of hydrogen with 16 grams of oxygen. Now, as per usual, you don't work with mass, you have to convert to moles. So we go ahead and we divide 2 grams of hydrogen by 2.016. Yes, 2.016 grams per mole, and you get 0.992 moles. You divide 16 grams of oxygen by 32 grams per mole, and you get 0.500 moles. And it's about this time that I realize I forgot to give you temperature and volume. You can't calculate pressure without temperature and volume, so let's go ahead and toss in that it's happening at room temperature, that's 20 degrees Celsius, and inside of a 2-liter container. Then we calculate the pressure exerted by hydrogen. The pressure exerted by hydrogen is just the moles of hydrogen times R times the temperature, which is, remember to convert, 293.15 Kelvin. And now I realize, goof that I am, that I have done my calculations with 0 degrees Celsius. Okay, so if you're taking notes, if you're just watching, go ahead and replace that 20 with a 0, and I guess this means that I get to learn how to put a thing on top of the screen in YouTube. Yay, learning experience. All right, anyway, so at 0 degrees Celsius and in a 2-liter container, 0.992 moles of hydrogen will exert 11.1 atmospheres of pressure. Then we do pretty much the exact same calculation for oxygen. Pressure of oxygen is the moles of oxygen times R times T divided by V. So half a mole of oxygen exerts 5.60 atmospheres of pressure in a 2-liter container at 0 degrees Celsius. And then to calculate the total pressure inside that container at 0 degrees Celsius, you just add the two pressures together. And that gets you a total of 16.7 atmospheres. That is an awful lot of pressure. I believe that's going to be the equivalent, I think, of 320 feet below sea level if you go diving. Closer to 330, maybe. 335, I don't know. Anywho, it's a lot of pressure. Now, the thing is, if you look at those two calculations, you'll see that we've repeated RT over V. Okay, so why do the exact same calculation twice with just a small change in between the two? Maybe there's a better way. Let's go ahead and see if we can't find one. If the total pressure is the pressure of hydrogen plus the pressure of oxygen, you rewrite that as nRT over V for hydrogen plus nRT over V for oxygen. And then, you see, you have the RT over V for each of them, so you factor that out. You collect your terms, and you get moles of hydrogen plus moles of oxygen times RT over V. Okay. Or to put it another way, what matters for a partial pressure problem is just the total moles of gas, not the different kinds of gas. This sort of thing shows up, not, all the time, but with some frequency. Sometimes all that matters is the total number of moles of stuff, and not what kinds of stuff each thing is. Later on, when you get to equilibrium, especially equilibria involving gases, that'll be a thing. So it bears repeating, it bears noticing right now. And let's go ahead and leave partial pressures behind, I think. Partial pressure problems are, alliteration aside, they're not super interesting, they're not super fun. Let's just go ahead and move on to discussing mole fractions. Mole fractions, not percentages, just fractions, are, just the fraction of each item divided by, the total number of items. Excuse me. To put it another way, you have the moles of one substance divided by the total number of moles of substance. Okay. The reason we use this, there are various reasons to take advantage of mole fraction. And we are going to try, hopefully, to look at a few of them. But first, let's work our way through an example. Somewhat familiar. We have our 2 grams of hydrogen and our 16 grams of oxygen. Let's go ahead and cut straight to the chase. We need moles. Obviously, if we're going to do mole fraction, we need moles. So that's 0.992 moles of hydrogen and 0.500 moles of oxygen. So what is the mole fraction of hydrogen? First off, this swoopy looking X is actually the Greek letter chi. Chi. Hi, how you doing? Chi. Okay. Why? Why not? It's fancy. Okay. So the mole fraction for hydrogen is the number of moles of hydrogen divided by the total number of moles. So it's 0.992 divided by 0.992 plus 0.5, or 0.992 moles divided by 1.492 moles. Okay. Columbus is sailing. Okay. Anyway, and that is equal to, when you do that math, 0.665. That's not too breathtaking. But I want you to notice something. Look over here on the left. You have moles divided by moles, and the moles cancel, leaving you with 0.665. Mole fraction is a unitless number. Okay, fractions and percentages are pretty much always unitless. But I wanted to go ahead and throw that in there. I wanted to remind you that it's a unitless number. That's one of the things that makes it kind of useful and kind of powerful in other ways. You can just throw that unitless number into other calculations and get interesting and useful results without having to worry about, units just messing things up. Okay, so let's go ahead and do the same thing for oxygen. The mole fraction of oxygen is going to be the number of moles of oxygen divided by the total number of moles. So it's going to be 0.5 divided by 1.492 gets you 0.335. No units. Okay. So it's these numbers shouldn't be, life-altering or earth-shattering or any other adjective for, change, big change. But there's something you should note here, and that's that you have a way to double check your work and make sure you didn't screw up. Because when you have mole fractions, just like percentages should add up to 100%, the mole fractions should add up to 1. So you add them together, 0.665 plus 0.335 is equal to 1. So yay, it worked. Okay, that means that my calculator is not malfunctioning. And we are looking at a mole fraction with just a mixture of 2 substances. Now, let's go ahead and take a quick jump back to this screen here. And before we move on to another application of mole fraction, let's go ahead and take a look at some more Greek letters. The second equation here, that funky-looking E thing, is actually the Greek letter sigma, the capital Greek letter sigma. And here it means that we're talking about a sum, that we're adding things together. So sigma chi I means we're adding up all the individual mole fractions. Okay? You add them all together, you should get 1. That's what that second line means. Okay, and now we're going to look at our third line where we combine mole fraction and pressure. What? Okay, well, what we're doing is we're talking about partial pressure. So follow along with me as I do a little bit of not too complicated algebra. Your total pressure, Dalton's Law is just pressure 1 plus pressure 2 plus pressure 3 plus all the other gases. That's just a way of saying, for an arbitrary number of gases. You could have any number of gases. But that means that, each pressure, of course, we're assuming it behaves ideally, is just nRT over V. Plus nRT over V plus nRT over V. And then we collect terms, and we just get that the total pressure is equal to mole 1 plus mole 2 plus mole 3, etc., times RT over V. I mean, this is nothing too surprising. This is just reiterating the point I made like 20 seconds ago, well, 2 minutes ago, that you add all the moles together, multiply by RT over E, you get the total pressure. Okay? Oh, it doesn't matter what kind of moles they are, it just matters the total number of moles. Awesome. Now, let's go ahead and take a look at mole fraction. Okay? Chi sub I, that's the mole fraction for some substance, is the number of moles of that substance divided by moles 1 plus moles 2 plus moles 3 plus ... or the total number of moles. Okay? This is just the definition of mole fraction. Shouldn't be too heartbreaking for you. But this is where things get interesting. And by interesting, I mean not super interesting. Okay, let's go ahead and multiply both the bottom, and the top of this fraction. Let's multiply that by RT over V. And we are allowed to do that because RT over V divided by RT over V is just 1. You can multiply anything by 1, and you're not changing anything, so it's perfectly acceptable. Okay, so just multiply by a fraction of thing divided by thing. As long as they're the same thing, you can do that. And if it gets you something interesting as a result, then hooray! And when we do that, we find that we have nRT over V on the top and the sum of the moles times RT over V on the bottom. Or just the partial pressure for whatever substance you're talking about divided by the total pressure. So that's two different ways of calculating mole fraction. You can, it's just the fraction of moles, or you could talk about it as the fraction of the total pressure. It ends up being more or less exactly the same thing. So instead of having to find a way to measure the number of moles of substances that you have, you can just measure the pressure of the substances. You can find a way to measure changes in pressure and things like that. And that'll tell you about the mole fraction, which is really helpful because pressure is a lot easier to measure than number of moles. You just need a pressure gauge, a barometer, or a manometer, whatever you need. Another way of looking at this is that the partial pressure of whatever gas you're looking at is equal to the mole fraction of that gas times the total pressure. So again, this can be a shortcut to measuring things. If you have some way of measuring change in pressure, a partial pressure for an individual substance, and you can measure the total pressure, you can get you can get the mole fraction. Or if you know the mole fraction and the total pressure, that gets you the partial pressure. Things like that. In other words, mole fraction and pressure are, nice handy ways of shortcutting in between different substances and ways of measuring the amount of substance present, so long as you know temperature and volume. So mole fraction isn't just something you have to learn. It's something that you can actually get some small fraction of use out of. And with that, we are once again bumping up on the 15-minute mark. So let's call it quits for this lecture and come back and talk more about fascinating topics in our next lecture.